Many companies have placed their data centers, and there's a real danger that hospitals and such within that state will lose power because the data centers are being prioritized. So biology is a very different research culture to, say, computer science. It's much more collaborative, but I think it's a lot to do with the teachers, Yeah. And I do remember the geography teacher being incredibly boring. And so geography was the subject I willingly gave up very early, well, not very early, at 14, I think. So as computer scientist, I think actually in some ways it was a bigger shock to the community than me being a woman. I think in terms of science potential brought about by AI, I'm extremely positive. I think it will accelerate discoveries, because much as we're told that a lot will be taken over by AI needs human supervision.
Welcome to this fresh episode of KPIT STEM Dialogues. And today it's my privilege to welcome Professor Jane Hillston to this conversation. The path that she has chosen and the work that she does is remarkable in many contexts. Her research areas are broadly three. One is stochastic process algebra, and she will talk more about it, especially when it comes to performance evaluation process algebra, what is called as PEPA. She also works in the area of quantitative verification techniques and model applications. So let me turn to the core problem that she addresses. It's a problem relating to getting a certain level of service as a customer of any type when there is a restriction on the resources again of various type. So supposing, you and your friend are sitting together and you want to order pizza from the local store to be delivered to your place. You want the pizza hot and fresh. You want it very quickly. On the other hand, the pizza company is concerned about how many people they need to employ to kind of bring the pizza to you. So how do you balance in such a volatile situation the requirements of service on one end and the ability to provide resources at the other end? And now this is a problem that you see not just when you're ordering pizza, but this is a problem that you see when you're trying to catch a bus, a problem that we see in our automotive architecture about the nature of computing power and the networking power that we need to supply. So it's a problem of the world, the desire of getting a certain level of service in the context of the constraint on resources. How do you do that in a very scientific and mathematical way is really the core area that Professor Hillston addresses. So I would like to welcome you, Dr. Hillston, for this episode, and thank you for taking time for us.
Thank you for that example in terms of the pizzas. I think it's very good example because it's really relatable, and that's very much the core of what I'm looking at, is that balance between service providers and service users to find the happy medium where everybody is satisfied sufficiently, perhaps not quite as quick as they would like to get their pizza, but fast enough that it's still warm, and the cost on the company is not so high that it's unsustainable for them, and the cost of fuel is kept manageable as well. So there are many different aspects about this trade-off, and that is what I try and develop techniques to help people understand where their trade-offs are and how to find a satisfactory balance.
So tell us about what got you interested in mathematics. What was your family background like? Was mathematics a normal, dinner table conversation in your home?
Yes, I mean, to some extent, yes. Neither of my parents went to university, but they were both quite comfortable with mathematics. My father worked in accounts, and my mother also worked, she was a bookkeeper and managed the salaries for a small factory. So I wouldn't say we had mathematical conversations, but certainly mathematics was something that was valued and held up as a good thing. So there was no fear of mathematics in my family. And from an early age, I showed a lot of aptitude, and that was something my parents encouraged. I really loved reading and writing, particularly writing and expressing myself. And I was quite surprised when my school selected me to actually take part in something called the London International Youth Science Fortnight. And that was absolutely transformative for me. It was a great program of meeting other young people from all around the world, and being presented not really with solutions, but with the problems in science. So I remember we went to chemical distillation plants, and people explained to us the need actually for efficiency in those processes, but also safety. I think we had talks from a company that was running the railways, and again, issues there about scheduling and things, and many different aspects of science and maths were presented to us in a very engaging way, and we were encouraged to contribute our ideas to what solutions might be. Even though we were 17 and relatively untrained at that point, it was really empowering to feel that we had a role to play. And I really credit that fortnight that I got to go to London and meet all these people with shaping the rest of my career, because, as I say, it opened my eyes to how I could contribute through having an ability in maths to all sorts of core problems of society. It also, for me, opened my eyes. As I say, my parents hadn't been to university, to this international world that science makes you a member of. And that's been a really core part of my development and real enjoyment of my career, is those opportunities to interact with people from all over the world, find, common problems, work with them, but also in the side, discuss their lives, their issues, what it's like in their country. And that's greatly enriched my life.
We have seen evolution of computer science from a very early days to AI, and you still see areas of applications of performance evaluation techniques to now AI from a very different dimension, right? So what keeps you going? What is your secret in terms of what habits or routines that you follow that keep your curiosity ticking?
Very basic ones that I learned at school, I would say, reading and writing. So I do try and set some time aside for just curiosity reading. So a lot of the reading I do is driven by different roles I have. So I may be evaluating, I may be supporting somebody's CV, and therefore I read certain things with a definite purpose. But I do try and make sure that a couple of times a month I just browse. And I won't necessarily read all of a paper. I'll read part of it. I'll read the abstract. I'll chase from one. I read one and it's citing something else, and I think, oh, what's that about? And I'll go and look that up. So I think creating that some space for curiosity, and it is harder as you feel the pressure of you need to keep publishing and things. And I think we're seeing that not enough people are doing that. And then the other habit I try and keep is writing. I love writing. It's I think it's a skill that is invaluable regardless of your topic, because whatever you do, and also probably regardless of your career, but certainly within science, it doesn't really go anywhere until you write it and explain it to other people. So it's really important to have good skills in writing, and to, I think, have empathy of putting yourself in the position of your reader, because when you've worked on something for several months and you finally got the proof and you finally know how it works, you want to tell somebody something, but they may not yet be quite in the position to understand that. So you need to think about of how to bring them on that journey with you. And I think ensuring that you have good writing skills is something that you have to practice. It's not, if you don't do it for a long time and then you sit down, your writing would be a bit clunky, just as mine would be if I tried to play the piano now after about 30 years of not practicing.
you started in mathematics and then you switched to com science. And so
Yes.
what was the switch from maths to com science?
So the work I did, so the highest maths I did was the work I did in the US, which was on a topic called algebraic topology, which is a very beautiful abstract theory of how to represent kind of shape an organization. But at the time, it was very much an abstract theory. It had no practical applications. I'll come back to it does now have some. But this is looking at multidimensional surfaces and understanding where the gaps are and how things can be transformed from one to the other. And I really loved this. But I'm a deeply practical person. So I like to create tangible things that people can appreciate. And I like to have a positive influence. So I like to help people. And I did worry that if I pursued a PhD in algebraic topology, I would be joining a somewhat elite club of mathematicians around the world who work on this and talk to each other, but very few people outside that field understand what they're doing. And as I say, at the time, it had little impact. And so I actually then took a job as a programmer to learn more about computer science. At the time, I thought maybe it would be satisfactory. After a couple of years, I realized what I really like is to keep learning. And so a university was probably a better environment for me than a software house. And so then I moved to Edinburgh and did my PhD in computer science. So it was that feeling that it had a more immediate impact and better connection to people than this rather elegant but abstract area of mathematics.
So your specific area of research in your PhD in com science, what was that and how was that decided?
So because I'd been working, I actually took a position in the university as a research assistant. So I took a job, and so that constrained my area of research to some extent. So that job was looking at performance modeling. So this aspect of designing using mathematics to understand this trade-off between the needs of users and the needs of service suppliers. And the classical approaches to that are things like queuing networks, but they have certain limitations when you come to modern distributed systems. So for my PhD, I wanted to look at, are there better ways that we can do that from the point of view of distributed systems, as opposed to queuing networks are very good for classical kind of sequential systems. And because of my, I guess, abstract mathematics background, I started attending lectures at Edinburgh. And because I was interested in the performance side of things, I wanted a much more quantified view. So I wanted to understand, how long does that take? Okay, it's going to reach a termination state, but I need to know when. I don't just need to know it's going to happen eventually, which was the kind of classic view. So that was really the work of my PhD, was to bring in this background of stochastic modeling and understanding the behavior of systems and embed it within this rather elegant way of describing systems that previously had just looked at what systems do, but now could start to incorporate information of how long they take, what resources they need, these more quantified aspects.
You already touched upon the performance evaluation process part of it. So we looked at it from the point of view of the formal methods, but if you were to kind of approach it from a performance evaluation process, if we were to take it to, once again, to the young engineers of today, how would you describe?
Yes, so performance modeling is very much about use of resources and ensuring that trade-off between the service provider, whatever that service is, whether it's pizza or it may be delivering a decision that you need within the car, for example, whether the brakes need to be applied in an emergency situation. So there is some kind of service, and then we have a user of that service. And there are decisions that you make in designing the system of how much resource you put in to meet the needs of the users. But resources are expensive. They're expensive in terms of quite often initial investment, but they're expensive to run. They can be expensive in that the more components that you have more chance of breakdowns. You have more to maintain and to ensure that it's working correctly. And so we know that in a perfect system from the user's point of view will be one that has infinite resource. Okay, so there is, whenever I need something, it's like having my own personal server pops up and gives me the answer that I need. So let's say we're making a query to Google or ChatGPT. The answer comes back instantly because we just have infinite number of servers that can address my query and all the other millions that are going on across the world at the same time. And that's not how systems can really work, because we know infinite resource is not practical. And so we're trying to model that understanding. And so we abstract for the systems in terms of mathematics of what is the demand on the system. So how that's often termed in terms of workload. So if we think about the post office, it's how many customers arrive per minute, per hour. And then we look at what is the service capacity of the system. So in the post office, that would be how many windows do they have open? How many people are actually there to serve the customers? And then there are other aspects that you can bring in as well, which is how, when there is available service, how do you choose which of the people waiting gets to go to the front of the queue? In fast food restaurants, you will often have different queues in front of different servers, and you also have a different model in terms of the servers in a fast food restaurant, in that you have the customer facing server and then you have somebody back in the kitchen who's making the food. So you have essentially a two-stage service. So we have a lot of flexibility, even with the same physical resources, of how we organize things. And it's often not entirely intuitive what is going to give the better answer. So, for example, in terms of the post office versus the fast food, you can show with simple mathematical models that the throughput, so the number of customers that you serve in a unit of time, so which translates to your profit, is better in the fast food organization. Whereas the customer response time, the amount of what time you wait from when you arrived to when you actually get the answer and the service you need, is better for the post office. So these small differences can make a difference to whether you're satisfying the customer more or the service provider more. And that's a simple example. We're talking about just a small number of servers in a single unit. But often what we're looking at are large software systems with these kind of decisions being made at many different levels. Or we're looking at a single software system that has thousands, hundreds of thousands, or even millions of users. And your intuition, unfortunately, just doesn't extend to that great parameter space of how do we organize all these physical bits. And so that's where the mathematical models come in from a performance point of view and let you test out which one is actually going to give me the better response time or the better throughput or the better balance between the two.
We all know that in the last few years, AI has taken the world by storm. And you see it in multiple areas. I mean, you see the billions, or I should say hundreds of billions of dollars getting invested in it. You see trillions of data points captured in these systems for their large language models. So you have a situation where enormous resources are being created, enormous data is being organized and managed, and a large number of queries are being addressed. This, I would imagine, is probably like a perfect area where your methods can be applied. So how do you see the applications of these, of your methods in this scenario? And what do you see as the importance of addressing your methods to a world of AI. So how do you look at this overall scenario? How do you see the contribution of your field in making this issue making this a better solution for humanity as a whole?
I think it's really important, and I am trying to engage more of my colleagues within the performance evaluation community to look at it from this point of view. Like many areas of science, they've become quite fascinated with the application of these models to their own problems. So what we see in the performance community at our conferences and such is lots of people using now large language models to describe to get assistance in building models, and instead of using the mathematical techniques, using statistical techniques to try and understand systems. And as I said at the beginning, for the user, it's always better if you have infinite resource, or it's not really infinite, but as much as you could possibly want. Yeah. And that is what we're seeing play out in the industry for a large extent. And this was why, in a way, DeepSeek was really exciting when it came along, because they were working in an environment of much more constrained resource. And they resorted to a lot of traditional, if you like, performance approaches, often based on engineering rather than perhaps mathematical methods, but really understanding their system in terms of its resources and trying to produce the same answers with less resource. And they showed great success in that. I think going forward, there are challenges for us to apply the mathematical techniques to systems of the scale of the large language models and other generative AI, because it is way beyond the scale of the types of systems we normally model. But there are approaches that we can use. And so I think the key thing is to start looking at that. So, for example, there has always been an approach of looking at a system, and when there is a lot, as there is a lot of data, thinking of it in terms of a fluid. So instead of trying to model all that data moving through the system item by item, you think of it as a flow, like a fluid within pipes. And just as, it's important for plumbing as well to ensure that the flow is as good and as efficient as possible, we can take that approach as well with these large models. And that's the kind of approaches that we're starting to see developed. But it's a very exciting area from the point of view, it needs new maths, it needs new approaches, it may need a new process algebra because it is beyond the scale of anything we've looked at before. But equally, it's crucially important because, as you say, we're witnessing systems going into wide-scale public use that are really quite profligate in terms of the energy. There's the carbon consumption from when they're in operation, but just the number of chips and things that are being used and bought. And so you've got that manufacturing costs, you've got everything else, the amount of water that is used. And although many of the large tech companies are aware of this and seeking to reduce their carbon footprint, and they're looking at how they generate energy, they're not tackling the fundamental issue of, is this really the best architecture for solving this problem? And also, is this the best tool for this problem? So a lot of the time, I think we're using a very complex tool for problems that really don't need that complexity. And there is an environmental cost in doing that we all need to be alert to, because the climate change is a real thing, and we don't want to accelerate it any more than is already happening.
I completely concur with you, actually. I mean, it's like a great suction pump, which is taking all the resources from the world. And, now they are looking at all kinds of ways in which energy can be generated. I don't know at the end of this, how many nuclear power plants we'll end up having.
Yes.
I don't know what would be the distribution of energy generation across the world, and even within a country, across the segments of the population. I think
exactly.
It's a very, very critical problem that we all need to be very conscious of, and we have to apply our minds to solving that problem.
Yeah,
Very-
there was a paper in Nature earlier this year looking at Virginia, the state in the US, where many companies have placed their data centers, and there's a real danger that hospitals and such within that state will lose power because the data centers are being prioritized.
There is an evolution of underlying mathematics and also the notation, what you call as a language, right? Which also sounds like you have domain specific paper, right? So there is a base paper and then there's a domain specific paper. I have just one follow-up question on that. I'm trying to connect paper and the formal methods and the mathematical nature of the notations and ability of general people to write that down and understand and interpret and work with it, right? It may not be intuitive and natural. Do you see application of Gen AI techniques to express this in language, but translate that into paper for systems to work with it? But the people are also able to express more comfortably so that they don't have to, quote unquote, let's say, work this or understand these notations.
Yeah, so it's not something I've done myself, but as I said, I've seen a lot of papers this year appearing in conferences of people using the large language models to provide that natural language interface towards formal methods of different types. I would say with varying success.
Okay.
So certainly one paper that I reviewed earlier this year, I think they said it was sort of 62% successful. So I think we're still at the stage, as we are with a lot of the applications of generative AI, where it's a good productivity gain to give you a first cut at something, but you would still need somebody who actually understands to come in and correct it and make sure it's really doing as anticipated. Part of this is because of data. There's not a lot of data out there that's suitable for the language models to learn from. So I read a second paper where they had explicitly tried to fine-tune a model towards a particular style of modeling, and that was a little better. I think it got to about 80% good models, but still 20% of the models really just weren't good. The really worrying ones, because I say we use something like a compiler, so when you put a model that's badly formed, it will spit it out and say, this is not a good model. What's bad is when it is a well-formed model, but not a model that makes sense in terms of describing the system you want to describe. And there you really need human expertise to spot the difference, so you can't rely on tools. But I have a colleague who is actually tackling a slightly different problem, but still a very important one. So what she's looking at is legacy computer systems. Many organizations have large computer systems that nobody quite knows how they work anymore or how to update them. But nobody dare touch them because they're crucial for the operation within the organization in what way. And so she's now trying to train an LLM model to read the code and work back to natural language descriptions and then develop the key elements so that somebody can understand what needs to be replicated. So there's all sorts of ways that we can bring large language models to bear within our problems of getting more reliable systems.
So speaking of AI, a lot of AI work today is fundamentally inspired from neurons and how the neurons work in the brain and the connections between neurons. And that's kind of closer to the biological systems you have worked on, in terms of applying performance evaluation methods for those. And in your research area, you have seen varied kind of systems from transportation systems to biological systems. So which of these came across as most fascinating or something that really caught your interest and was really, really fun to kind of work with?
So I must say I've not looked at neurons as such. I'm sure that's fascinating too, but I did really enjoy learning about biological sciences. So the work I was doing was looking at processes within cells. And one of the pieces of work we were doing was trying to understand circadian rhythms. So how we all organisms, plants we know particularly, but all of us respond, and every cell in our body responds to the light and dark cycle that we experience daily. And understanding the biochemical process for that and how it can go wrong was a really fascinating thing to do. So we built some models. So the biologists were carrying out experiments with plants where they were putting them into very controlled environments and changing the length of their day. And so they would change so that some of them were on 12-hour days, or some of them would have perhaps an 8 hour of darkness in the day, 2 lots of 8-hour light, or vice versa. So they would think, and then looking at that and then trying to work that back to understand what it was in the processes within the cell that allowed these responses to the light. So that I found really interesting. I liked biology at school. I just liked maths more. So it was great to have this opportunity later in my career to go back and learn a little more. So I just studied textbooks and I went to a lot of seminars and talked to my collaborators and really fill in another level of knowledge from my school level into, I'm not a researcher in biological sciences, but I have a good understanding of that area of biochemistry and application towards the circadian rhythm, and learn that new stuff. And you learn about the science, but you also learn about the culture and the way that science is done, which is quite different. So biology is a very different research culture to, say, computer science. It's much more collaborative. It much more depends on a team and the different considerations. I mean, learning to understand quite how difficult it can be to get data points in a biological experiment. Whereas I think as computer scientists, we assume data's just there because we can generate it really easily. We have systems spewing out data all the time. If we're looking at distributed systems, we have all sorts of ways of monitoring the traffic and the results and the throughput and the output. And then you go to biology and people spend days, growing cells to get certain results. And that was really interesting. And so I feel it's always enriching. I enjoyed working on the transport systems too, because that took me into a different domain. So not so much with scientists, but we were talking with city planners. And actually in Edinburgh, it was the bus company was sponsoring the bike sharing system and talking to them. I'd previously done work with them on modeling how the bus system works and how to try and optimize their scheduling and planning, and then looking at the placement of bikes sharing stations and understanding that was also fascinating because we were doing it in Edinburgh. I could actually see the bike stations from out my office window. So it was very very satisfying to see that direct translation of the work you're doing into practical aspects.
I want to take you back to your school days. I heard you say you like languages, you like mathematics, you like biology. Was there anything that you did not like in school?
Geography, I think. And that's really ironic given how much I really love my international life now. But I think it's a lot to do with the teachers.
Yeah.
And I do remember the geography teacher being incredibly boring. And so geography was the subject I willingly gave up very early. Well, not very early, at 14, I think I gave up geography. But no, as a child, I was fascinated and still am very curious about all sorts of things.
So, Proceedings A, it's like a 200-year-old magazine. And you are the first female editor-in-chief of that. So tell us about what you feel about that.
Well, I feel incredibly honoured and proud. It really is an honour to be given guardianship, because I think that's what, as an editor-in-chief, you're looking after it for a temporary time, and I will pass on to the next editor-in-chief. So a journal that has such history and so many fantastic discoveries within it, to have the current life of that journal, as I say, under my guardianship, and developing new initiatives and trying to carry it forward in a way that's respectful to its history as well. So I think just generally being an editor-in-chief for Royal Society Journal is an immense honour. Being the first female, I think has been interesting. There has been a little reaction from some in the community. I think also because I'm a computer scientist, and I think we're a very broad journal. We bring in, traditionally it's been very much about the application of mathematics to other areas of particularly physical sciences. So we cover chemistry, geosciences to some extent, earth sciences certainly, physics, not biology because there are separate journals for that in the Royal Society, but many different engineering. We have a lot of papers from engineering. And so in the past, the editor-in-chief has been from one of those subjects or from mathematics. So as a computer scientist, I think actually in some ways it was a bigger shock to the community than me being a woman. But I think it's really important, because and I recently wrote a short blog post about this, because when I was studying mathematics as an undergraduate, we were told mathematics is the queen of sciences, which is I don't know, I remember one of my lecturers joking and saying more like the handmaiden, because mathematics is put to use by all the other sciences. Fundamental advances often rely on applied mathematics within those disciplines. But I think now we're seeing the era where that will be AI. AI is an immense tool, or has immense potential as a tool for other sciences. So much as I have reservations about the current implementations and how well they are being developed with a view to sustainability and long-term impact, I think in terms of science potential brought about by AI, I'm extremely positive. I think it will accelerate discoveries. We need people to understand how and when to use it, but it's there. And I think what we will see in Proceeding A, we're already starting to see, is an increasing number of papers that are not so much applying maths into the other domains, but applying AI techniques into the domains. So it won't displace maths, but it will exist there alongside it.
So you have been a strong proponent of women in science. You have been the winner of the Suffrage Science Award. What do you think is the current status of women in science, and how much change you have seen over the years? And in your opinion, what more needs to be done to attract more women to science?
I think things are better. I think that I would say that things are better than where they were. It's always a little bit difficult because obviously my position has also changed. So when I started my career, I was a woman, but I was also quite junior. And there were certainly situations where I felt disregarded, not heard, overruled, felt that was quite often on the basis of my gender rather than the content of what I was saying. Now, having been in positions of power, of being the head of school for the largest computer science department in the UK, it's to some extent a brave man who would try and overrule me or speak over me in a meeting. So my perception has certainly improved immensely. But I think more seriously, talking to younger colleagues, I think there is less overt discrimination and disregard for female colleagues, certainly within computer science. But I think less overt, it's still there. And it's not just computer science, it's across all the disciplines, that there still are certain assumptions that are not inclusive about working practices, assumptions that are made that when you have a child, that you're somehow not committed in the same way, which is not applied to fathers, but is often applied to mothers. There are assumptions, sort of tacit knowledge about what your capabilities are. And I think there's still a dominance of believing that leadership has to be in a certain style and with a certain mannerisms, and women are sometimes discussed as being too soft or, not tough enough for leadership. And I think that's quite wrong. Just because we do it in a different way doesn't mean that we're not effective. So I think we have made progress, but there's still much to do. What can we do about that? I think it's about calling out bad behaviors. So I think we have to challenge, and it has to be not the underrepresented group that's doing that challenging. I've seen this myself, particularly with women, that if you challenge a behavior, you're almost playing into the stereotype of being a difficult woman or a hysterical woman or an over-emotional woman. There are lots of different ways in which legitimate concerns can be minimized by belittling the person who raises them. So I'm really a strong advocate for the need for champions, sometimes now called allies, and that people take up the concern of underrepresented groups. I try and encourage male colleagues to be the one that when a woman's spoken over in a meeting, or a woman expresses an idea and a minute later a man says that idea and everyone goes, oh, that's fantastic, that it's another man, not a woman, who steps up and says, but Jane said that first, or that's what Jane said 5 minutes ago, because it has so much more weight when it's not the minoritized group or the underrepresented group doing that. And I think this applies across all the different areas. So with ethnic diversity and nationalities and such. And I think often people don't even realize they're behaving badly. They're in the in-group. They don't even think about other forms. It's like I mentioned, the style of leadership, the style of communication. People need to be more alert to these things and ensure that they're being inclusive. Maybe that means taking a little bit longer. Or I really encourage people when we're organizing conferences or things and there's a session chair, take a question from a woman first if you can, because it really empowers the woman to hear another woman's voice, whereas you tend to get very eager men booming out at the beginning, and women can retreat a little bit from that. But if you have a woman first, it can help balance that out a little bit. So I think there's very practical things that people can do, but mostly it's about awareness and just being alert to these opportunities. It's about when you're making decisions, designing processes, designing programs for conferences, taking that little bit longer and thinking, what are we missing here? The number of events I've been to where there's a panel and it's all white men, and then you challenge them and they say, oh, I didn't notice because the person organizing it was a white man. And you just getting people to think, okay, we've got our panel. How representative is that? And just taking that little bit longer on decisions, I think could really help start to be more inclusive. And then we wouldn't need to keep talking about it.
You said that you head the largest science department in the UK. So I want to ask you some question from a student perspective. In the current times, what kind of faculties you would want an engineering student to develop, especially now that we know that there is a deluge of AI that is coming in every aspect of thinking of students. As you know, there was recently a study done at MIT which showed that the cognitive abilities or the memory abilities, the recounting abilities of students are going down because of the usage of AI. So what abilities would you advise students to develop in the context of, in the current context?
Yeah, I mean, I think the abilities that we always did seek to embed within our students. So beyond the immediate technical knowledge of a particular programming language or a particular technique, say in engineering, it's to critically think and question the world around you. And that unfortunately does mean you have to have the ability to read complex information and make your own judgments on it. It really actually worries me when I see, even in PDF viewers now, there's a little thing in the corner that says, do you want an AI summary? And it's very tempting to people to just sort of skip, but then you miss the nuance. You might miss the one thing that is really important to understand, or it may be that there's something that you would really object to if you read it in detail that you don't get in the AI summary. So I think I would really encourage students still to develop their critical ability through reading and analysing. And I think that extends to the mathematical skills of analysis and applying logic and even programming. Because much as we're told that a lot will be taken over by AI, AI needs human supervision, and you cannot supervise something if you do not understand what it's doing. I recently talked to some colleagues in law, and it was really interesting. They're very concerned about the application of large language model techniques to routine law work. And everyone can see that it's fairly formulaic, drawing up contracts, settling certain things to do with conveyancing and buying houses or whatever. And it's an area where AI can work quite well. But it's also currently, or has been, where trainee solicitors developed their skills in writing and understanding and negotiating. And so if you hand that all over to AI, where are you going to get the trained solicitors with the experience to oversee the AI from in 10 years' time? And they have a real worry about the training pipeline. I think other areas haven't thought it through quite so much yet, but I think many graduate level jobs where people say at the moment, oh yes, you can hand it over to AI, it will still need it will need human supervision. And the only way you become skillful in anything, we know, is through hours of practice. And so I would advocate that all students practice their critical abilities and not use AI unnecessarily. Use it as a partner, but don't hand things over to it.
So quickly moving on to the next part, what we call as a rapid fire round,
Okay.
just a small.
This was the bit that filled me with trepidation when I saw it on the program.
No, it's really a handful of questions and I'm sure you will deal with that pretty easily. So the first programming language that you learned?
Pascal.
Pascal, interesting. And
so sorry, that just shows how old I am. But yes, it was Pascal. And then I learned C.
Pascal and C, yeah. I think same, because during my engineering days, it was similar. The next one is, what was the first paper application that you wrote?
Oh, the first Pepper model. Probably something very small, because in process algebra, there's a tradition of modeling vending machines. So I probably built a vending machine model.
Mathematics or computer science?
What for? I mean, for pure enjoyment, mathematics. For actually having an impact on the world, oh gosh, I've got to be careful. I have all my Proceedings A board to answer to. I think for having, my route to having impact on the world is definitely through computer science rather than mathematics, bearing in mind I gave up proper mathematics as my discipline in my 20s.
Book that changed your perspective.
Oh, probably Robin Milner's book on process algebra, Calculus of Communicating Systems.
Interesting.
Anything not related to a technical subject? Any other book?
Any other
Non-fiction?
book? Well, I'm a big reader of fiction. Trying to think one that changed my perspective. Oh, probably War and Peace.
Oh, is that so?
Okay.
Yeah.
And maybe the last one, if you weren't a computer scientist, what would you have chosen?
I'd be an author. I think I would, or a writer of some sort. Yeah.
Fantastic. Thank you very
interesting.
much.
Very interesting. Extremely fascinating. Thank you very much. Really appreciate your time.
Well, thank you so much. It's been a lovely experience. I really enjoyed it. So thank you for the opportunity.
Thank you. Thank you.
Thank you.
Bye-bye.
Bye. Bye.
Bye-bye.